Hello everyone and Assalamualaikum and welcome to our presentation. We are from the Matcha Latte group and today we are presenting our project called Designing a Daily Diet Requires Balance in Nutrition Using Linear Programming. So what is this project about? So basically we want to find the cheapest combination of food that still meets all daily nutritional needs like protein, vitamin and also minerals. This is a classic problem in mathematics called diet problem, and we solve it using linear programming. So before we build our own model, we conduct a literature review and we found that this problem has been studied for decades, starting with simplex method involving into mixed integer linear programming and now even using machine learning for complex decision. But for our project today, we applied the classical approach using two tools, which is the Microsoft Excel Solver and also Lingo. Um, Today we are going to present the introduction and also problem statement, followed by a quick literature review to set the context, a demo showing how we use Excel Solver and Lingo, result and discussion, and finally share our conclusion for this project. Without further ado, let me introduce you our teammates.
Good day, everyone. So, before we head into our presentation for the day, which is our LIP project, let me introduce our team members from Matcha Latte. Firstly, Zatul, Wong, Saumya, Hakim, and Hana. Malaysia offers a wide variety of traditional and modern food, but selecting a daily diet that meets nutritional requirements while maintaining a healthy calorie intake can be challenging. Excessive calorie consumption is often associated with health issues such as obesity, diabetes, and cardiovascular diseases. Therefore, it is important to identify an optimal combination of food that satisfies daily nutritional needs without exceeding recommended calorie levels. This study applies linear integer programming (LIP) to optimize a Malaysian diet by determining the most suitable combination of selected food items. Using nutritional data from commonly consumed Malaysian food, the model aims to support healthier dietary planning through mathematical optimization. Designing a daily diet requires balancing multiple nutritional requirements, including calories, protein, fat, carbohydrate, fiber, and sodium. Many food choices may satisfy one nutritional requirement but fail to meet others, making manual diet difficult and also inefficient. The challenge is to determine the optimal quantities of 14 selected Malaysian food items that meet all recommended daily nutritional requirements, remain within acceptable nutritional limits, and also achieve the lowest possible calorie intake. To address this problem, a linear integer programming model is developed and solved using optimization tools such as Excel Solver and Lingo to identify the minimum calorie diet that satisfies all nutritional constraints.
Hi everyone, my name is Noriza Tufatin binti Mama Shukri and my matrix number is 2250757. So today I'm going to present about the literature review where the literature on linear programming has evolved remarkable over the decades. It all started with the classic diet problem where researchers sought to find the cheapest combination of food that would still meet all daily nutritional requirements. Things like vitamin, mineral, and also protein. Early solution relies on the simplex method and tools like MS Excel Solver that made this calculation accessible to a wider audience. As the field matured, it expanded into mixed integer linear programming, or also called as MILP, which added the ability to handle discrete decision, like whether to include a food item or not. What is truly mind-blowing is that modern solvers have becoming nearly 4 million times faster since 1990, making it possible to solve problems that were once impossible. Today, researcher is pushing even further advanced decomposition method like Danzig-Wolf and also Benders are using to break massive problem into small pieces. And machine learning is being integrated to automatic complex solver decision like branching and cut selection. In shorts, the literature shows a clear trajectory from planning a single healthy meal to solving a massive industrial scale challenge. And for our project, we built a directly on the foundation by applying these classical techniques using Excel solver and also Lingo.
Everyone, my name is Wong Chun Hao and my matrix number is 2250777. So today I'm going to present about the demo Excel solver. First, click the file and go to options and then scroll to adds in. Make sure you select the Excel adds in here and go, and also click the solver adds in if you haven't clicked yet, and then click OK. After that, go to data tab and you will see your a solver appearing right here. So then the next step will be entering your data set. So this is my food data set, and from cell C2 to C15 are my decision variables, and the row 17 is the sum product formulas, and row 18 just a reminder of my limits not used by solver directly. So the third step will be entering the formula at the total index row. So I actually did it. So all this is my formula, sum product C2 to C15 and C2 to C15. So all this is my formula. So go to the next step will be open the solver dialog, and then at the set objective part, actually click D17, cell D17, and I'm doing minimization. So click minimization by changing variable cells is from C2 to C15. So all this is my constraint. I set it previously already. And then the important part is doing the simplex LP. After this, click solve, click answer and sensitive, and OK. Okay, so then the answer report one will be appearing here, and then the most sensitive report will also be appearing. So that's all for demo Excel solver. I will be presenting the Lingo solver. So step one, we will be writing the objective function. So the objective is to minimize the total calories, and the formula in math is minimization equals to 390 times x1 plus blah 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 until here. So here is the objective functions. Minimize total daily calories. So the numbers 390, 300, 600, 550 are the calories value per serving of each food. And then the x1, x2, x3 are the decision variables of how many serving of each food. So after the objective functions, write subjects to then all your nutrients rules. Each rule is one line ending with semicolon constraint. So this is the constraint for protein, and this is the constraint for fat, and this is the constraint for carbohydrate. Constraint 4 is dietary fiber, constraint 5 is sodium, constraint 6 is calories, constraint 7 is also calories. The difference between each another is one is lower bound and the other one is upper bound. So now I will be explain all this with the exclamation mark. It's just a remark. It's non-related with the model. So lastly, this is our complete Lingo code with the full model. So then you actually can, I will teach you guys how to run it. Now you click solver and solve. So this will be the solution report. And then, so now if you want to know the sensitive report, you click solver and you click range. So now the sensitive report will be coming up. So that's all for demo Lingo.
Assalamualaikum, Dr. Sharifah and everyone. So today I'll be presenting our results and discussion for our linear programming diet model. So let's take a look at my first slide. Our primary objective was to minimize total daily calories while satisfying all the nutritional bounds. So after processing our 14 Malaysian food option through the optimizations software, the model determined that the absolute minimum caloric intake possible is exactly 2000 kcals. To achieve this, the software chose non-zero serving values and for only 3 specific food items. As shown in the table, the optimal menu requires 5.51 servings of white rice, or which is around 5.5 bowls, and then 0.67 servings of grilled chicken breast, or which is about 67 grams of it, and 7.23 servings of banana, which give us roughly 7 whole bananas a day. Every other food item, from heavy staples like nasi lemak and mee goreng to lighter options like milk and oatmeal, was assigned a value of 0 and completely excluded from the menu plan itself. Moving on to slide 2, here are the direct screenshots from our software outputs showcasing the cross-validations between Excel Solver and Lingo. If we look closely at the Excel section, the final value column explicitly calculates our optimal breakdown of 5.51 for white rice, 0.67 for chicken breast, and 7.23 for bananas. On the right side, the Lingo report displays our constraint ranges. For example, if you look at the bottom section, labeled right-hand side ranges, Lingo references our constraint by rows. Row 7 represents our 2000 kcal lower limit, and row 8 represents our 2500 kcal upper limit. Both software environments achieve identical results, validating that the mathematical framework we formulated is completely consistent and correct. Now, let's discuss our final slide of our today, which focuses on our sensitivity and ranging analysis. This analysis explains why the model behaves the way it does. If you look at the Excel constraint screenshots, the lower bound calorie row has a shadow price of 1. This represents a direct 1-to-1 relationship with our objective functions. It means if we decrease our minimum calorie limits by 1 kcal from 2000 to 1999, our total minimized calories will also drop by exactly 1 calorie. In Lingo, this matches up with row 7, where our current right-hand side value is 2000. Lingo shows that this constraint has an allowance increases of 500 and an allowable decrease of 9.61. All our other nutrient constraints like fats, carbohydrates, and sodium have a shadow price of 0. This tells us that slightly tightening or loosening those nutritional boundaries right now will not change our final calorie score, because the solution is currently locked down entirely by the 2000 calorie floor limit. And finally, let's look at for our real-world evaluations. While the linear programming model worked perfectly from a mathematical standpoint, it highlights a classic problem in nutritional optimization, which is creating an illogical diet. So in reality, sitting down and eating 5.5 bowls of white rice, over 7 whole bananas, and just a tiny 67 kilograms of chicken breast every single day is completely impractical. This menu lacks essential meals variety, leaves out crucial micronutrients from standard vegetables, and forces a massive carbohydrate surplus of over 443 grams. These extreme food combinations happen because our basic model only applied lower bounds for health requirements, but lack individual upper bounds, or maximum caps, or specific food portions. To make this model realistic for a Malaysian lifestyle, future versions should introduce restriction constraint, such as capping banana consumption to a maximum of 2 units per day, so the solver is forced to distribute the food choices more evenly. Well, that concludes our results and discussion section today. Thank you very much. Let's take a look for our discussion.
In conclusion, the optimal solution achieved the minimum target of 2000 kilocalorie using white rice, grilled chicken breast, and bananas. While this solution is mathematically optimal, it is not realistic because it lacks food variety and contains excessive carbohydrates. Future improvements should include food limits, dietary balance, and budget consideration to make the diet more practical for everyday use.